Good morning. Good afternoon. My name is Will Mars. I'm the founder and president of Endurica LLC. Been enjoying all the talks this morning. Electric cars are certainly a game changer. We live in an exciting time. Trying to wrap my head around all the ways that end uses of rubber are changing and all the opportunities that are opening up. Of course, lots of things are changing, but rubber is always going to be there. What else is there that can take all the shock and the vibration and survive like rubber does? But now we are completely redoing, for electric cars, for example, suspension, chassis. We've got to carry around heavy batteries. We're getting rid of these big internal combustion engines, and we're going with electric motors. We're rethinking every part of the car, including the rubber parts. And we're also measuring everything that happens in the car, right? Sensor technology is exploding. We want our cars to be smart. We want the car to be connected. We want the car to look after itself. And we want the car to, or all the rubber parts, to keep their structural integrity. We also need to talk about simulation. There's a big expansion going on right now in how we use simulation. In the past, simulation has really been a tool for developers only. If you look on the left-hand side of the slide here, you can see the traditional development loop. We can do a prototype build and break, and we can use a simulation to do this virtually. That helps us go through the cycle faster. It helps us reduce risk. And the idea is, with a simulation, the ideal is to try and get the design right on the first iteration. Every car maker, every part maker these days is using simulation because of the value that's in the get right first sort of philosophy. And this is not just a research thing. This is in people's production engineering workflows. And that's all well and good. Simulation has a new role to play. So it's not just going to be on the development side, but also on the operation and the use side of a product life cycle. So, for example, road load data from your car can be uploaded to a virtual twin, and we can track damage accrual in a part. The idea is to give owners more information, give them more control, give them more reliability, right? Just-in-time maintenance, no more surprise failures. If you're a company and you own a fleet of cars, surprises aren't good for business. So imagine what this means for owners of fleets of vehicles. So there's this idea of a digital twin and having a digital copy of your physical asset that you can sort of easily access information about structural integrity of a rubber part. And so what I want to show you today is a prototype digital twin for a rubber mount that could be used in an electric vehicle. So how close to this vision do you think we are? Let's assume that we can get displacements or loads off of the car frame. There's existing sensor technology for that, right? Assuming we can do that, what barriers remain? Well, first of all, we're going to need to be able to take those displacements or loads and convert those into strain history, stresses and strains on the part. Now, traditionally, finite elements can do that very well, although that's traditionally been a very slow process. So that's one barrier. Another is that we're going to need to be able to do a fatigue analysis, and of course, rubber fatigue is it has to involve certain nonlinearities, certain special effects. We have some fatigue solvers that can do that. We're going to need to be able to iteratively update the damage state every time we get a new sample of the latest displacement or load history. So that's another barrier that we're going to need to get past. And then finally, all of these things, we're going to need to be able to do them in real time. Okay, so let's dive right in. In order to get a twin up and running, there's two phases that we're going to need to go through. In the first phase, we're going to sort of implement and initialize the twin, right? Get everything set up so we can run it. And then the second phase is actually running the twin. Now, in the implementation and initialization phase, there's really two big tasks that we have to do. The first one is to address this barrier with the finite element, right? When we're running the twin, the finite element analysis is not going to run fast enough to operate in real time. So we need something faster that lets us convert from loads and displacements into stresses and strains on the whole part. And we're going to use a tool called Endurica EIE. It's what we call an interpolation engine. And the basic idea is that you use your finite element model to model a series of pre-computed finite element solutions. We store those, and then that becomes a nonlinear map between displacements and strains, and we can evaluate that map very, very rapidly. We've done benchmarks, and we can hit speeds of about 10,000 times faster than a finite element job using EIE if we've pre-computed the solution. So that's one thing we're going to do to get set up. The other thing we're going to do is we're going to initialize residual life by means of a standard load case. So we're going to have some standard load case that's sort of nominal operation of the part, and at time zero, before we've accrued any history, we're going to ask the question, how many repeats of that standard load case can the part endure? And then as the part accrues actual loads, we're going to use that standard load case as a measuring stick to quantify remaining life in the part. So in the example I'm going to show you, I'm running all of these examples on my laptop. We're going to do this live for you. You can see it's a couple years old, but a good spec, but nothing crazy. 2.9 gigahertz, 6 cores, 32 gig of RAM, running Windows. So the finite element model that we ran to implement the nonlinear map is shown here, right? So it's a model that has something like almost 30,000 finite elements. These are solid continuum hybrid elements, and we've also used membrane elements on the free surfaces to increase accuracy of the plane stress condition. Right, cracks in this part initiate on the free surface. In this model, there are 64 time steps, and we'll talk a little bit more about that in the coming slides. The total solve time on this is not quite 3 hours. So those 64 time steps in the solution for the nonlinear map are laid out here. You can see that we are running a 4 by 4 by 4 grid, right? 4 increments in the X direction, 4 in the Y, 4 in the Z, and I've kind of laid out on this plot you're seeing on the left-hand side. That is the actual path that the finite element solution follows, and you can see it's basically just mapping out the entire XYZ displacement space. On the X channel, we can go plus or minus 12 millimeters. Same on the Z channel. In the Y, we can go from 0 to 5 millimeters of compression on the part. The animation that you're seeing here is the model going through all of the different grid points, and we're going to assume that when we operate our digital twin, that this envelope of pre-solved solutions, that envelope includes all of the strain history, right? So when you run the model, you want to run it to extremes so that all possible loading states are enclosed within the set of grid points that we've run. After we build the map for interpolation, then we need to go ahead and initialize residual life on the part. We use Endurica CL to do critical plane analysis of the standard load case. In this case, the standard load case is a single compression, right? No X load, no Z load, but just a single compression to 3.75 millimeters of displacement. And when we run the simulation, we use Endurica CL uses a technology called critical plane analysis. For our critical plane analysis, we've done the calculation on 17 planes for each element. And basically what we're doing is we're assuming that a crack could take any orientation, and we're looking for what's the crack that gives the shortest life. When you do this analysis for this mount under the standard load case, before accruing any damage, this part has a residual life of 386,227 repeats. So now we have our interpolation map set up. We have our digital twin initial residual lives initialized. So we're ready to go ahead and start operating the twin. I'm going to show you an example here in just a sec. As we're doing the example, we're going to follow this digital twin updating workflow. So you can imagine that when you press the go button, there's going to be a data acquisition system that's going to go and collect loads off of the car, and on some periodic basis, we're going to stop the recording. We're going to take that recording and send it off to the process, and then immediately start the recording again. And what we need is for the analysis of the prior recording to be completed in the same time or less time than the amount of time that's spent doing the data acquisition. That way we can keep up and do this in real time. When we send the data acquisition information, first step is going to be to send it to our nonlinear map. EIE is going to use the map to interpolate the loads and produce strain history for every finite element in the model. Once we have the strain history, we're going to pass that to our Endurica DT fatigue solver. We're actually going to run two jobs. The first DT job that we're going to run is going to accrue the damage in each element that occurs because of those strain histories. When we run that job, we write out what we call a restart file that contains the damage state for every element in the model. Then we're going to run a second DT job. We're going to, starting from the current damage state, which is recorded in that restart file, we're going to take our standard load case and we're going to say, starting from this point, how many repeats of the standard load case would it take to run the part out to failure? Now that's kind of a hypothetical because it assumes a certain kind of load history going forward, but that's what we're going to use as the measuring stick of residual life. We'll also be able to look at crack length as a function of accumulated increments. And then we can pass out the residual life and the crack length for each element in the model. We can display those on a dashboard, and we're ready to start the whole process. So let's go do it. All right, let's do this. First thing I'm going to do is kick off the digital twin interface. Right, this reading here is the number of repeats of the downward standard load case, 3.75 millimeters down. Also going to launch the Windows Task Manager so we can watch the CPU. There's 6 cores, so when it's pegged, that means you're running on all 6 cores. So for the first load step, before we bring in real data, let's do a few kind of verification cases. So the first thing I want to do is just load up let's do the standard load case, right? So we're going to do a 3.75 millimeters downwards displacement and just a single cycle. And what we want to see is that we produce a decrement of 1 repeat in the residual life, and that's exactly what happens. So I do 3.75 millimeters down, I get decrement of 1 on the cycle. So we could also say, well, what if I do a heavier load, right? Instead of 3.75 millimeters, what if I do, say, 5 millimeters, right? Well, so here we go. I've just hit the update button, loaded up the data. Here's a single cycle, 5 millimeters down. And what this is telling us is that the 5 millimeter down load case has decremented the residual life by 3 repeats of the standard load case, which, if you remember, was 3.75 millimeters. So, and you can see this is the plot of residual life versus the data file that we've uploaded. In the first one, it went down by 1 cycle, and now we've gone down by another 3 cycles. So this is the displacement history. This is the residual life history. The contour colors that you're looking at, these are colors right now showing the residual life at each element in the model. You can see that the red is, the deepest red is occurring on the inside crease here. So as we load in compression, we're seeing cracks on this inside radius. In addition to looking at residual life, we also could look at change in crack length. I like that view. Let me update it here. I like that view because it sort of better highlights where the most recent damage is occurring. And so you can see, again, it's on that inside crease. We're seeing a crack growth of something like 8 times 10 to the minus 7 millimeters of growth. As we're going through this, also notice these lights. These are showing you run time, right? How much time is spent in EIE, how much is spent in DT, and how much is spent developing these graphics. Also before we go on, I'm going to put on a little bit of background music for your listening enjoyment. Thought I would play Mars, the Bringer of War. How's that for a background? So let's play that. Okay, so right, we validated that it works for a bigger load. What if we do multiple repeats, right? Instead of doing one repeat of the standard load, what if we do 10 repeats of the standard load? Well, I hope it would decrement by 10 cycles, right? So here's 10 cycles, and here's a decrement by 10 standard repeats of the load. And you can see the count has gone down. You can see we haven't really changed the failure mode because we're just pushing harder in the same direction. Fine. What if we do something a little bit different now? What if we go ahead and push in the plus X plus Z direction? I've got a data file here where we've set that case up, right? We're going to push 12 millimeters in the plus X direction simultaneously with a push 12 millimeters in the Z direction. So let's go ahead and run that, right? 0 to 12, a single cycle. Now this has a little bit of a compression on it, right? It's got the standard 3.75 millimeter compression. That's the green line. And now in this case, these lateral loads that we've just imposed, they don't really decrement the residual life counter, which maybe doesn't surprise because the damage that's going to happen isn't necessarily the same as what we were seeing before. Now we don't see any damage on this back face, but before we move on, let's check the front face of the mount. So I'm just going to rotate the view by here, and what you can see is that we've done some damage on this corner of the mount, right? So if we're pushing in the plus X direction and in the plus Z direction, that means these three corners are in compression, right? They go more into compression, but this corner goes into tension because of the lateral load that we've applied. And so that's the corner that gets the most damage. That makes sense. Let's set the view back to the front face. And now we pushed in the plus X plus Z. Let's push in the minus X minus Z and see what happens. What do you think will happen? Well, so here's our right load downward in the minus 12 directions for X and Z. Here's our Y direction load static at our 3.75 millimeter displacement. And you can see that by pushing back in the other direction that, let's see, I want to make this 15 degrees. Now on the front face, after we've done this in the other direction, now we're seeing the opposite corner also getting some damage. So I've got tension damage that happened on this corner and on this corner, right, on opposite corners, because I did plus on the diagonal and minus on the diagonal. These two other corners really have very little damage on them at this point. Let's, as a next step in the demo, do a circular motion in the XZ plane. And so I'm going to go ahead and load that load case. You can see it's just two sine waves, one shifted by 90 degrees, right? The Z channel shifted from the X channel by 90 degrees, again with a static displacement of 3.75 millimeters. And you can see now we're developing damage on all four corners of the mount, as you would expect. This circular motion does induce some damage. We've done 5 repeats of the standard load case worth of damage by this measure. Okay, so now we've done some relatively simple things. Let's do a more complicated thing. I've been playing the Mars, the Bringer of War. Since I don't have a car to upload signals from, let's use the audio source as our source of loading for these channels. So I'm going to go ahead and I'm going to grab 1,000 samples of the whole song. I'm going to do this with no preload in the vertical direction on the part, and go ahead and run that. And so you can watch the timer. I'm going to put a little timer here. You can watch the timer for 1,000 samples of the song, and you're going to see a decrement here once this finishes computed. You can see we're pegging Now we're really making the computer work hard. Still solves in a very reasonable amount of time, couple of seconds. And you can see that the equivalent damage that we've done is about 3 cycles. Three standard repeats of damage is what the Holst song does to the mount. Now this was with 0, right? The green line is at 0 millimeters. What happens if we put a little bit of compression and play the Holst song into the mount? Let's do that again, and that's this one right here. So let's go ahead and play that. Here's, by the way, a picture of the Holst signal in the XZ plane. You can see it has a little bit of an offset towards the plus X, plus Z direction. So, it's going to be a little bit more damaging on the first corner. Well, I guess it would be the corner that we have to turn around to see the worst corner. So I'll do that right now. Right. So here's the corner that's kind of getting the worst of the Holst signal, and you can see the damage that has developed. So that's been a quick primer in the digital twin prototype that we've developed. Thank you. So my message for you here today is that digital twin is here now. We built this prototype twin using commercial off-the-shelf tools. The only custom thing is the dashboard, and that's built out of very lightweight, well-understood pieces. We talked about the implementation and the operation side of doing this. We talked about the compute speed, and right now, using just in our prototype phase, we're already up to a speed of better than 0.03 of a second per data point. In the last 2 years, we've achieved a 10 times speed up in our code, and we have some new things coming in the pipeline, and we fully expect to get more than a factor of 10 speed up again over the next 2 years. Follow us on social media if you want to track how we're developing this. We use the hashtags GetDurabilityRight and Winning on Durability. Thank you for your attention.